Thank you very much for inviting me and for the nice introduction. Thanks to everyone for showing up. So, do I start or we wait for the doors to? Yeah. Okay. Okay. So I chose today to speak about one relatively simple topic. It's one of the things we do. We're also doing other work on ring superfluidity, ring traps, and 2D Bose gas, and non-equilibrium physics, and so forth. But I think it's better to focus on one thing and go hopefully slowly enough and explain things well. Nevertheless, when I think I'm explaining things well, this still might not be true. So please, okay, fine, I forgot. Yeah. If Bill is not faster than you, you can interrupt yourself. So I assume a vast majority of people in the audience are somewhat familiar with cold atoms. Is that? Yeah, it's a lot of nodding. Okay. Okay. So I'm gonna talk today about our experiments on uniform Bose gases, and this work was done in collaboration with these 5 people. The doctors on the left are people who have PhDs, but they're not really postdocs. One of them is what we call a Royal Society University research fellow, and he's been my kind of main partner in crime for many years now. And Nir is a junior research fellow at Trinity College, and 3 PhD students, Alex, Igor, and Tobias. So this was my sort of safety slide, but it's probably not necessary here. So at the beginning of our experiments, we do what everyone does here as well, and in many other labs around the world. So we use pretty much standard methods of laser cooling and evaporative cooling in order to make some Bose-Einstein condensates. And this is the machine on which all the experiments we'll talk about today have been performed. And if you are an experimental student, and then you might appreciate this is quite simple. I mean, these are actually 2-inch mirrors, so it's maybe a bit bigger than you first thought. But still, it's about a yay big machine, which can still do something useful. It's rubidium-87. So now to the topic of my talk. As you all know, since your undergraduate studies, there's only 2 kinds of potentials in physics. Right? And there's the harmonic one and the square one. Sorry, this was me not being used to this clicker, so I clicked too soon. And this is, in undergraduate physics, this is true because these are the ones we know how to solve. But it's true actually even a bit more broadly, even when you think about it more deeply. These are qualitatively the 2 basic situations. Either you do have a special point, you do have some local minimum around which the expansion will tend to be harmonic, or you have something which does not have a special point, which is translational invariant, which is what usually happens in condensed matter systems. And so in the field of ultra-cold atoms, with harmonic traps, many people have done many wonderful things over the last 20 years or so. Probably, I don't custom make this slide for every institution, but but here I think there's a good chance somebody recognizes themselves. Okay. Anyways, so on this side with harmonic trap, a lot has been done over the last 2 decades. A lot of beautiful things. And on the other hand, with the uniform, with the box potential, basically nothing has been done until very recently, right? Despite the pleas of some theorists, especially those who came to us from condensed matter background. And this was before my time, but as I understand, they did whine quite a bit back in 1995 why we're making a harmonic trap and not the box potential. But they eventually, they quit whining because we convinced them that it's not possible, and that's a good reason to give up. But then things have actually changed, over the last 20 years. Various technology matured and various ideas matured, and so a couple of years ago we realized that we are actually within sort of shooting distance of making a uniform system as well, and that's what I'm going to tell you about today. So to spell it out slightly more, the long-term kind of motivation for going into uniform box potentials rather than harmonic ones is mostly related to condensed matter physics-like problems. So there's a large class of problems related to phase transitions and critical behavior, which is fundamentally better to study in this kind of system. And it's not, when we do stuff in the harmonic trap, then what we do is we invoke the so-called local density approximation. We say that the density varies slowly enough, and so somehow you can have a local homogeneous like system with some bulk properties, and then somehow that gradually varies across the trap and maybe gets averaged out. And that a lot of the time is wonderful. It works great using the LDA, the local density approximation. But occasionally, for some important problems, it is not. And it is either because you're simply washing out the signal by making global measurements which average out over your density, or more fundamentally, because the LDA breaks down. And in particular, it breaks down close to phase transitions, because close to phase transitions, you have the divergence of the correlation lengths, right? You have critical behavior where the system is supposed to behave in some sort of scale-free fashion, right? And so if you have a harmonic trap, you're artificially introducing a length scale, which is the oscillator length of that harmonic trap. Anyway, so there's a bunch of things related to critical behavior and the dynamics of spontaneous symmetry breaking, such as the Kibble-Zurek physics, that fundamentally is different in a uniform system than in a harmonic trap. Then still in sort of solid state land, things like transport and propagation of sound over large distances, again, better to do in a uniform system. Another topic that is now very much in fashion, and a lot of it has been done on it both experimentally and theoretically here, towards the work on topological edge states with cold atoms. Here again, uniform systems are quite beneficial. My last point I'm going to mention briefly is in some sense more practical, but still might open the door to new physics, which is that when you make a BEC in a box, as will become maybe more apparent through the talk, then you actually make a Bose-Einstein condensate at about 100 times lower density than in a harmonic trap, simply because there is no condensation in real space. There's no bunching up of atoms at the BEC transition. And if you have about 100 times lower density, you have about 10 to the 4 times lower three-body recombination for the same scattering length. And so that's sort of a doorway towards going to higher interaction strengths without losing equilibrium. In some sense, it's related to the old story of how we went to very dilute gases and very low temperatures in order to make a BEC. If you work at progressively lower and lower densities, then the importance of low body interactions is higher than of those involving more particles. Okay, so this is by way of some really long-term motivation. I'm actually not going to show you any of this stuff today. We're just at the beginning of this game and exploring some simple things. And in some ways, we're going back to 1995, or in some sense, we're actually going back to 1925, because we're seeing some things actually closer to Einstein and textbook theories than was possible with a harmonically trapped gas. So this is the outline of my talk for today. I'm going to tell you a bit of practical stuff of how we make bosons in box potential and how we have achieved condensation in this system. And then I'm going to tell you a little bit about two different kinds of studies which are studying the first kind of round of basic properties of the system. So this part is related to thermodynamics, so to behavior of the gas relatively close to the critical temperature. And then the very last part is focusing on the BEC itself, on the coherence and ground state properties of the condensate. Okay, so this is our optical. This is our box potential, which is optical. Is depicted here. So the way we make a kind of a square well-like potential with a uniform zero potential inside is using an optical box, which is really green, as shown here, because green light is repulsive for the rubidium atoms. Actually, for most atoms, it's repulsive. For most atoms that we work with, it's repulsive. And so we construct a box where the green light forms the walls of the box, and it's just dark on the inside. Okay? As you can see here, our box is made from one long tube, which is actually a sort of optical vortex. It is made by imprinting a very large phase winding onto a beam. So you have kind of a centrifugal barrier for photons, which creates a flat potential in the center. It's like a 24th order zero in the intensity. And then that long tube is just capped off with two sheets of green light. Right? And so the shape of the box is cylindrical, but the shape could be anything, right? The point is just the potential is uniform on the inside. Shape could be anything, but for some practical reasons that people in the field are familiar with, we initially chose to work with something which is elongated, because then you can see the anisotropic expansion of the BEC when you release the cloud from this trap. This is the picture of the atoms inside the box, and you see the scale here. So we can vary, of course, the size of the box, but our typical box is something like 60 by 30 microns. Okay, now the way we make this box, this is a bit of optics. The way we make this box is we use this device depicted over here, which is called the phase-only spatial light modulator. And this is one of those technologies that I alluded to before that has just developed a lot, over the last 20 years and is now allowing doing some fundamentally new physics as well. So the spatial light modulator is basically kind of like an LCD screen. You paint something on it, and you draw something on your computer, and you send it to this device as a screen. And what it does is basically that depending whether this is white or black or something in between, it changes the index of refraction of this LCD device pixel by pixel. Okay? And so using that, you send a simple Gaussian beam on it, right, and you can imprint some phase. Okay? You can imagine it's just going through. It's actually done in reflection in practice, but it doesn't matter. You can imagine it just goes through a faceplate where every pixel of the faceplate is independently controlled. So you can imprint some phase on it, and then as the light propagates further, then in the Fourier plane, you create some intensity pattern. Right? So the goal is just to be very good at Fourier transforms, which is not always easy, but the concept is relatively simple. And so we actually use just one of these devices and a clever student. And in order to program something, which is actually exactly what is shown here. I mean, this pattern that is shown is the one we use in our experiments. So we programmed this or this student, Alex Gond, programs this in a very clever way. So that you can send a single Gaussian beam onto this pattern, and what the pattern does is splits this beam into 3 and makes one of them a tube and 2 of them sheets and sends them in opposite directions, right? Then you just need a couple of mirrors to align this onto your atoms. Now, as a curiosity, as we have learned gradually as we were experimenting with this heuristically, sorry, I'm jumping ahead. Let me just show you that it does work before I tell you that it shouldn't. So basically, this is what you want to make. You want to make 1 tube and 2 sheets, right? And this is what you make in practice. This is what they look like. Now, as a curiosity, when you think a little bit about what we are doing, it's highly unkosher, and it's not meant to work. And the reason it's not meant to work is that basically any single pattern you want to make, you can, if you're good enough with somehow numerically finding the appropriate phase pattern that will create this pattern in the Fourier plane. The problem is that then we want to use it as a toolbox, and I say, like, okay, you know how to make a ring, you know how to make a sheet, now give me a couple of these and one of these and send them in different directions, right? And if you want to combine different things like that, if you want to have basically this toolbox where you can just combine different shapes, right? Then you would think like that what you do is someone want to superpose these different phase patterns in order to simultaneously create different beams, right? But there's a problem with that this is called phase-only spatial modulator, okay? You cannot actually change the intensity of the beam. You can only change the phase. And if I want to superpose 2 things which individually have modulus 1, then the sum actually does not have modulus 1. So in order to really do that, I would have to change the intensity of the beam, and I don't know how to do that because the device cannot do that. And so we do this dirty trick, which was invented by Alex, but probably reinvented, because I'm sure there's, optics is a very old field, and I'm sure there's engineers who have figured this out before, where we take this function that we really want, and then we take just its argument and put that into the exponential, okay? And so now we have something which in some funny way seems to contain the phase information, but has eliminated the problem that the intensity, the amplitude is not 1 over here. This thing here has a modulus 1. And this turns out to work very well, as you can see up here, which is somewhat surprising, but one can show in a very simple simulation that indeed this is true, even though it's maybe not bringing you that much closer to understanding. And so this is related to a phenomenon which we sort of colloquially call phase dominance. So let me show you what I mean by that. So you have 2 pictures here. One says phase, one has amplitude. Okay? And these are both real pictures. They're in real space. but they're unreal also in the sense that their phase here, depicted in the back plane, is just constant, right? So this is the amplitude, spelling phase, amplitude spelling amplitude, and the phase is just constant. These are real numbers, okay? And so I Fourier transform this. I Fourier transform this, and I get something that is hard to detect by eye what it means, but this is the Fourier transform of it, and this is the amplitude distribution, and this mess in the background is a phase distribution, okay? And then I do something ridiculous, okay? I take the amplitude from this bottom thing over here, and I take the phase from the top thing here, and I wet them together, okay? And so this is obviously meaningless. It's not a Fourier transform of anything, okay? Just took the amplitude from one complex field and the phase from the other complex field, and you put it together into rubbish, okay? And then you Fourier transform this back, and you get the phase, okay? And you can do this with people's faces as well, right? I mean, it works with anything, right? Yeah. You will always recognize that the person whose face you took will, in the end, dominate in the final picture. And so this kind of a phase dominance, basically you can screw up the amplitude as much as you like. If you get the phase right, you will get pretty much the right thing in the Fourier plane. Allows us much more freedom in order to create the potentials we want using only phase control.
So is the idea then on the amplitude you just put something uniform in, or?
Yes, because we can't do anything but, right? Because this thing, we send in the Gaussian, well, I mean, some broad Gaussian, and that's what it is, right? Yeah. Okay, so we know how to make a box with the tube and two sheets, right? Now we want to make a cold gas in the box, and so one first difference that you realize compared to the harmonic traps, which go on forever, right? I mean, up to arbitrarily high energies, the box has a fixed volume, okay? And so in order to stuff the gas into the box, you have to somehow pre-cool it, right? I mean, it has already to be, your cloud has to be small enough and dense enough in order to shove a good number of atoms inside the box. And so what we do is we pre-cool in a harmonic trap just like everyone else to something like 100, 200 nanokelvin, something pretty cold. And then basically like in this cartoon here, and then once the thing is small enough to fit, this is still a harmonically trapped gas, but it fits into the shape of the box, then you turn on the optical box and you turn off the harmonic trap. There's one slight technical detail that the optical potential we create is 0 inside the box, but there's also gravity, which is a linear potential, right? So if you did this in the presence of gravity, we would not be in a uniform system, right? We would be in a linear system. And so you have to cancel gravity at about 10 to the minus 4 level with magnetic field gradients, which we thought was a bit daunting, but it's not. It turns out that it's pretty easy to do. Okay, and so once you have it in the box, then you can do further evaporative cooling, just like we're used to in a harmonic trap, just by lowering the height of the walls of the box. So this is just the pictures of the cloud before and after, and these green lines is what you expect to see if the system was uniform.
Do you do a 3D evaporation? You take all walls down?
Yeah, so the these are two different questions. So because of the technology we currently have, so we use this one spatial light modulator which makes the whole box, and you cannot put any intensity control into the beam after you have phase shaped it, right? So we have only one AOM before the spatial light modulator, so we're reducing everything in proportion, okay? But a priori, we decide whether we want the tube to be the bottleneck or we want the walls to be the bottleneck. And actually, in that sense, we do, I guess, 2D evaporation, because we choose the tube to be the slightly lower, because if you fall out of the tube, you're gone. Whereas if you leave through the walls, you still get stuck in the tube, and that can mess up the images afterwards and confuse the analysis.
It's a single AOM driving all the beams?
It's a single AOM, yeah. Before the SLM, yeah. SLM is spatial light modulator.
Yeah. Do you get fringing between the beams when they cross?
Ah, okay, that's good. It's a very good question, and it anticipates another viney question that might come later. So sometimes theorists ask, still not happy. They say like, so why do you make this cylinder instead of a nice rectangular thing, okay? And so for a rectangular thing, you would need 2 AOMs and 2 SLMs, which is a question of $30,000, $40,000. I mean, it's not, too much. So that's why we use the cylinder, because you have just two beams. And so with polarizations, we fix that problem, right? So the tube has one polarization, and the two sheets have a common polarization, but they're very far apart in terms of their width, right? So the wings don't touch each other, right? And if you wanted to make a rectangular thing with 6 instead of 3 beams, then you could not do it just with polarizations, right? Then you would have some potentially holes at the corners where some funny fringing happens, right? So you would have to do it with frequency, and then you need to double the equipment, or triple ideally, if you want full control.
Is there some reason in principle that you couldn't put AOMs after the SLM?
Yeah, I mean, it's a bit hard to do such a good job with the SLM not to change I mean, it's really sensitive phase information, right?
No, just after everything's over, you've got your separate beams, your tube and your sheets.
Yes.
And then is there any reason why you couldn't massage them afterwards?
Well, but I mean, the AOM would have to perfectly reflect the first order would have to be perfectly identical to the input, right? That's never quite true, right?
Well, yeah, that's true. So,
I mean, if you put it on a sheet of paper, you say like, oh, this still looks pretty Gaussian. That's okay. It's okay at that level, but this is quite sensitive. Yes.
You want to avoid the additional distortion.
Yes. Especially at some intermediate point where you're neither pure phase nor pure amplitude. Where you're neither in phase plane or in intensity plane. Right? No. If there was you could maybe put a very good attenuator, which uniformly somehow just removes the amplitude, right? But the AOMs are not that good. I mean, when you have a funny shape. But it's not, again, I mean, it's not a big technological problem to just have 2 or 3 separate AOMs and spatial light modulators. Okay, and so we put it in the box, and then we evaporate. And actually, if you make a quasi-pure BEC in a harmonic trap, we can load it into the box and it still be partially condensed, even though you do lose some phase space density, even theoretically. Even if you do it adiabatically, you lose some phase space density when you go from a harmonic to the box. But we didn't even want to do that for the first studies, because we wanted to make sure that the BEC we have is not a remnant of the harmonic trap. We wanted to start with the thermal cloud and do evaporation in the box. And then you already see how this is different from the harmonic trap, because in a harmonic trap, condensation occurs in both real and momentum space. You can take pictures in situ. As you cool the gas, it shrinks. BEC rises in the center. Whereas here, if you look in situ, nothing happens, or at least nothing good happens. I mean, all you see is that you're losing atoms. Right? You don't see any benefit of it, right? Because the cloud is just thinning. Okay? But then if you just release that in the usual sort of time of flight, then indeed you see that at some point a Bohm model distribution develops, and also the BEC expands anisotropically, because we have chosen this shape in order to have this anisotropic expansion as the signature. The bimodality is a bit trickier than in harmonic trap. Yeah.
Now, I'm trying to get a sense of how flat it is, and certainly this is one way.
Yeah.
Another way might be to ask, what is the size of the transition region between, say, zero potential and highest potential, like maybe the 0 to 90% point? How wide is that compared to the region where it's flat, or how much volume?
Yeah.
That is, how many atoms are in the places where the potential is, say, 10% higher than
Yes.
the light? Can you give us those kinds of
Yes.
numbers?
I can give you many kinds of numbers, but some look better than others. So I was asked exactly this question by some Physics Today person or something like that, and I think it worked out to more than 80%. Whereas in a harmonic trap, it's less than 20%, I think. That is within 10% of the... No, this was not in terms of potential, but in terms of density. If I define some average density, what fraction of the atoms is within 10% of that density? And I think it's more than 80%, whereas in harmonic trap, it's less than 20%. That's one figure of merit. But I will mention other ones. We'll almost stop doing it now, or at least we hope to stop doing it soon. But right now, almost everything we do, we try to be very careful to also look at the possible deviations from the uniformity. And so this is what I mentioned here at the bottom. If you look at the actual momentum distribution of a degenerate but non-condensed gas, you can figure out what kind of potential it is being released from. Because in a degenerate gas, once you don't have Boltzmann-like factors, but Bose-like occupation numbers, there's actually some sort of entanglement between the spatial and the momentum degrees of freedom. And once you integrate out this spatial degrees of freedom, the momentum distribution, the shape of the momentum distribution is affected by it still. This is this polylog functions basically that we use all the time, right? Where you say, G3 halves is is for 3D harmonic trapped, the momentum distribution, and G2 after you take the picture and so forth. You can figure out what G fits best, and put some bounds on how flat your potential is. And because it is pretty flat, then the leading order in the sort of Taylor expansion, the leading order is some high power law, and you want to estimate what is that leading order. And so in our first estimate over here, we got that it's something better than R to the 10, say. It was R to the 13 plus minus 2 in this assessment. And for most studies, you really, this is as good as uniform, but still we keep checking how to quantify this. Okay, so we have a BEC. Now we did some very, very basic thermodynamics checks first. So you see at some point BEC appears, you see what TC is, you want to compare it with theory, and now the theory is quite simple. You say the box is this long and this wide, you multiply it out, you see if it works out. And it works out. So that's just one point. Then next thing, we looked at the scaling. This is again kind of the difference between what we are taught as undergrads and what we also all know as called atom people. So if you have a uniform system, the critical atom number should scale as T to the 3/2, where T is the temperature, unlike the harmonic trap where it's T cubed. And here you see two red lines, the solid line and the dashed line. And now we should remember which one's which. The dashed one, they're very close, as you can see. But so the dashed red simply assumes that we have a perfect box. Okay? And then the solid line is much, much more work in order to somehow iteratively, self-consistently figure out what could be the deviations from the flatness of the potential. And now, this was also 6 months later, and now we are somewhere R to the 20, as an estimate to the leading order correction. Okay? And so, okay, this is basic textbook stuff. But while we were doing these things, we came to the first surprise of a uniform system Bose gas, already while doing seemingly trivial things. So when you're doing this kind of thermodynamic measurements, often you want to do a measurement where you keep the temperature constant and vary the atom number, okay? Because it's a clean kind of vertical or horizontal line in some sort of phase diagram. And there's a standard way to do this because there's always losses in the system, be it 3-body or 1-body from vacuum or whatever. Then you usually adjust your trap depth just so that there's a little bit of evaporative cooling all the time, and that maintains the temperature while the atom number is decaying. And we tried to use this trick. But first of all, the BEC is very long-lived here because there's no 3-body, because the density is only 10 to the 12 instead of 10 to the 14 per centimeter cube. So the BEC lives for like 20 seconds. But also what we discovered is that no matter what trap depth we make, the cloud keeps cooling. And we couldn't stop it cooling. I mean, we were trying to adjust this thing, and we tried to increase the walls. And at some point, it's like, the so-called evaporation parameter eta was more than 20. This point, you need age of the universe to do evaporative cooling, right? And it's not that, but the gas just cools spontaneously. Not if it's thermal gas, but if it's already been partially condensed, and then you're just holding it. It keeps cooling spontaneously. The BEC doesn't go up, but the temperature goes down. And so we then realized eventually what it was in several iterative steps. So the first insight was that because we have no 3-body and basically no light scattering, we're sitting in the dark, the only thing we have is collisions with the background gas in the vacuum chamber, which is 1-body loss, which is also indiscriminate with respect to the energy of the trapped atoms. And so if you have only 1-body loss, randomly removing atoms from the system, then the average energy per particle in the system stays constant during this process. And moreover, because we are so dilute, the interaction energy is a very, very small fraction of the thermal energy. And so thermodynamically speaking, we basically have an ideal gas. And now I start to use words which one could have forgotten by now. I certainly had to revise a little bit. And if that is the case, if you have basically ideal gas, then the pressure is just energy density. And if the pressure is just energy density, then the enthalpy, E plus PV, is just proportional to the energy. And so enthalpy per particle during this process remains constant. And so what this process actually is so-called isoenthalpic rarefaction, which if you revise your undergraduate thermodynamics, has a pretty famous name. It's called the Joule-Thomson effect. So you're happy for a moment, but then there's still a snag, which is if you revise even better, if you turn the page in your undergraduate thermodynamic course, then you also remind yourself that there is no Joule-Thomson effect in the ideal gas. It occurs only due to interactions. But there is a caveat there, okay? So what was thought then is in some sense true. But what is actually correct is that there is no Joule-Thomson effect in an ideal classical gas. Okay? There is a Joule-Thomson effect, as I will explain over the next few slides, in an ideal quantum gas. And basically, like, very, very clearly, the way to think about it is that the Joule-Thomson cooling, which is what we use in refrigeration or liquefaction of gases, it's a big industrial process, relies on the fact that the atoms like to stick together. If the atoms like to stick together, or molecules, then upon their rarefaction, the gas cools. Okay? Now, there's two reasons the atoms would like to stick together. One reason is that there's long-range attractive van der Waals interaction, and that's the one that's exploited in industry. Okay? But it could be just as well simply because they're bosons, assuming they're already in the degenerate regime. And so on the next few slides, we will see we have explained this quantitatively, but then we discovered somebody else explained it actually a bit earlier. Specifically in 1937 it was. These two Indian gentlemen. One of them was actually from Cavendish. I mean, he was a Rutherford student. And the other one I don't know. And they wrote this very, very, very beautiful paper back in 1937 in Nature, which I reproduced here almost in its entirety. I mean, yeah, I have maybe cut out half, and that half is just as awesome, but just not directly related to the topic. So I'll read it for you. It says, in view of the numerous physical and astrophysical applications of the new quantum statistics, this is just after the discovery of this idea of bosons and fermions, it may be worthwhile to investigate the Joule-Thomson effect for a gas obeying Fermi-Dirac or Bose-Einstein statistics. Then this is the methodology section. The calculation is simple and runs on the usual lines. Okay? So that's done, okay? and then they say, the results obtained are quite interesting, okay? And so they calculate, both for bosons and fermions, but I'm showing you just for bosons here. They calculate basically what is known as the Joule-Thomson coefficient. Here, I is enthalpy. I don't know what the notation was at the time. But so this is the change in temperature per pressure at constant enthalpy. And they calculate what it might be in the coldest substance that they could think of, which was helium at 5 degrees. And they say, well, it's possible to push it up to something maybe like 0.1 bar so 0.1 degree per atmosphere per bar. Right? Which at the time they thought, like, it's not so optimistic, but it's maybe not so bad either, because it could be up to 10% of the usual interaction effect that is observed and exploited industrially. Okay. And in the half of the paper that I'm not showing, they also do things. It's really remarkable. They introduce some quantity they call A. Okay. Let's call this quantity A measure of a degeneracy of the system. And then you can check all the factors of 2 and pi, and it's what we all know as phase-space density these days. And then they go on to explain very wordily, even though the whole thing is a page and a half, how if this quantity A is conserved, then a degenerate gas remains degenerate, and a non-degenerate gas remains non-degenerate. And if you perform such a transition, then the Joule-Thomson effect doesn't occur because this is adiabatic and so forth. It's very, very nice. And actually, they also predict for fermions, it's the opposite effect, because fermions don't like to stick together. So it's, or calculate the same thing for repulsive interaction in the classical world. So fermion, it heats under isoenthalpic rarefaction. And this effect, again, I think has been reinvented many times and is known in solid-state physics. It's basically the fact that if you randomly make holes in the Fermi sea, if you have a degenerate Fermi sea and you randomly poke holes in it, that upon thermalization leads to heating of the gas. Anyways, so they've predicted this thing somewhat before us. But let me now explain it in very simple terms. So in order to explain this effect, I have to step back a little bit to remind you what Bose-Einstein condensation is in the simplest possible form. Of course, we know many mathematical forms to predict Bose-Einstein condensation, but this is sort of how Einstein thought about it in 25, and it's the cleanest way to understand the effect we see. So usually, when you do the maths, often you do the maths for fixed particle number and varying the temperature. And at some point, like you find the critical point, and then the condensate starts growing and so forth. But that calculation with fixed particle number and varying the temperature slightly hides a very simple fact that once you're in the condensed state, then the number of thermal atoms is solely determined by the temperature. And on top of that, you could have any number of condensed atoms, okay? But the number of atoms in the thermal cloud is exactly equal to the critical atom number for that given temperature you're at. Okay? And to make all this clear, it's simpler to make a graph where we actually keep the temperature constant and keep adding particle number. And here I'm plotting the number of thermal atoms, the number of condensed atoms, a varying total n, Initially, everything goes into the thermal cloud. Then we hit the critical point, and thermal cloud perfectly saturates and just stays flat, and everything else goes into the BEC. So this is a line of slope 1, and this here is a line of slope 1. This one is a line of slope 0. These are Einstein words from back then. As separation is affected, one part condenses, the rest remains a saturated ideal gas, okay? With the number of particles exactly equal to what you, to NC at all times. Okay, and so here we have something that is resembling Einstein's picture, so something like this should hold. There's actually some more backstory to this. I won't go into it in detail. But back in 2011, we actually discovered that even for very weak interactions, this Einstein saturation picture does not hold so well in a harmonic trap because of some weird amplification of the effects, some interplay between the harmonic trapping potential and the interactions. And this was explained also at the time by us. And sorry, again. And one can show that indeed, if you extrapolate only to the limit of strictly 0 interactions, then in a harmonic trap you also get this Einstein-style saturation. But now we have repeated the experiments in the box. And in the box, you don't have to do nearly as much work. It just nicely fits what you would expect from the textbook. Right? So this is the harmonic. Our new harmonic trap measurements with the theory built on our 2011 work and no free parameters. And this is the measurements for a box, where not much explanation is needed. Okay, so we have this saturation picture, and we're going to use it to explain the Joule-Thomson effect. So in a very cartoonish way, you can understand it with this Bose Tea party. So at the fixed temperature, we can fit only so many particles into this cool party here in the thermal gas, and then we have a bunch of sort of persona non grata people in the condensate. Okay, and a number of these could be anything. Nobody cares about them. And
the opposite from the usual point of view. Usually we think of being very happy to be in the
I agree. I also switch to that point of view occasionally. But here, for explanation, it's not a good point of view to have. And now we're going to start removing particles randomly, okay? So there's a background guy atom which is going to kill someone. And if it kills one of these, again, nobody cares, okay? Because if you look at thermodynamically, right, you can throw any number of particles in the condensate on top of the saturated number of particles in the thermal cloud. This doesn't change the total energy. It doesn't change the total entropy. It doesn't contribute to the heat capacity. It doesn't do anything. Okay? So I'm not going to even illustrate what happens when you kill this guy because it's nothing. Okay? On the other hand, if you kill one of these guys from the thermal cloud, now we have an inconsistent situation. Right? This cannot be equilibrium because we cannot have BEC if the thermal cloud is not saturated. Okay? So one of these guys has to get promoted to the party. And so now it has arrived at the party, but it's got no T, okay? So now they have to share the T, okay? And now everyone is moderately happy, but the temperature has gone down, okay? That's the explanation. All right. Now, we can turn it into a bit more detail. The top is still a bit cartoonish, but it just a bit more quantitatively shows what happens. So you remove a thermal atom there. Something has to come out of the BEC, but in this process, energy has to be conserved. So one of these guys also has to drop to this level. So basically, instead of having one here and one in the BEC, we have two at level 1. And now if you compare the relative occupations of the excited states, you see that the gas is cooled. And the maths, actually, for such a gas is shockingly simple. I actually put this on my fourth-year exam in atomic physics just a few months ago. And a good 5 or 10% of the class actually predicted the results of our measurements correctly. Yeah. It was guided, of course, but yeah, nevertheless. So this is the idea. We have E over, I'm going to go slowly because I think it's satisfying. It's very rare opportunity that you can do maths in the seminar, right, without being hated. So we have energy per particle is constant, okay? But the only guys that contribute to the energy are the thermals, okay? So the energy is basically N prime, the thermal atom number times the temperature, times some numerical prefactor, which we don't care about, divided by N. But we're saturated, so N prime is just equal to NC, okay? So this is just equal to NCT over N, okay? And now the NC, the critical particle number, scales as T to the 3/2, okay? So we have basically the T to the, if E over N is constant, then T to the 5/2 over N has to be constant, as long as you have a condensate. And so as you remove the particle number, the T has to decay as N to the 2/5. And so this is a general scaling prediction. It doesn't depend on what the initial exactly absolute temperature is or absolute atom number and so forth. You can scale everything to the initial temperature and atom number. This is the curve you predict, and this is our data. And here again, I have stopped doing it in relation to Bill's question. here, I put NC goes to T to the 3/2. For the imperfect box, we actually get NC goes to something like T to the 1.6 or whatever. And then you get slightly different, and those lines are, again, not distinguishable. So I stopped showing them. OK, we can also look at the number for this so-called Joule-Thomson coefficient. So in 1937, the hope was that there is a coefficient which is something like 0.1 Kelvin per atmosphere, so maybe observable. But it did it at 5 Kelvin. And now if you do the maths, this is dt by dp, but you can re-express it into dt by dn, because those are our natural variables with just constants in front. And you can simplify it even more and get that this line here actually corresponds to this, some constants, thermal wavelength cubed over the Boltzmann constant. And this goes as 1 over T to the 3/2. So their prediction was based optimistically on 5 Kelvin. We are now at 50 nanokelvin, which is about 12 orders of magnitude difference in the Joule-Thomson coefficient. So the Joule-Thomson coefficient we observe is actually something like 10 to the 9 Kelvin per bar. It's about 10 orders of magnitude higher than ever observed in a classical system. Which doesn't mean that this is very good for air conditioning company, because the heat capacity of our system is relatively low. Okay? I mean, you run out of your 10 to the 5 condensed atoms relatively quickly. But nevertheless, it's a fascinating number. OK, so that was about thermodynamics, which this was all close to TC. Temperature was an important part of the story. And now I'm going to look at the coherence and the ground state. So as Bill says, often we're quite happy to be in the BEC. So now I say this is the important part. And we looked at this in 2 ways. I will spend much more time on the second one, but we'll start with the first thing we did. So the first thing we did when we made this BEC, and we saw something anisotropic, but you've never done it before, so you have to be skeptical. So we wanted to check that what we have made is actually some sort of coherent object. And then this is the sort of experiment that you can do without getting up, or at least Alex can do it without getting up. So you just have to ask the student to reprogram something. So now instead of having 2 sheets, we have 3 sheets, and you make 2 traps. And the reason it looks funny like this with a small satellite BEC is that we wanted this guy to be exactly the same as in the rest of the experiment, and then just added an extra guy, because this was time of paranoia. And so you make a BEC in both. This is basically kind of a satellite BEC for referencing things. You let it go, and you get nice fringes. They look a bit different than what we're used to with point sources. You see this kind of chirping of the period from left to right to right to left. And the reason for that is that this guy has such low energy that it expands so slowly that basically expands only in this direction, whereas this guy runs through it, expanding more isotropically. And so the phase variation along x is actually quadratic rather than the usual linear that we get in two-point source interference. Anyways, you can show it analytically, but you can also just numerically simulate, and you see that you do get this tripling of the period. So anyway, this was our first qualitative proof that this thing is coherent. And this is something we will come back to. Maybe we have not done so much on it now. It's actually quite possible that the system we have made will have some benefits for trapped atom interferometry, because it inherently has some advantages. I mean, it's a dark trap, so there's no differential AC Stark shifts to worry about between the 2 sides of the trapped interferometer. There's no 3-body loss, okay, so the BEC can live forever. And also because the interaction energy is so low, because the density is 100 times smaller than a typical BEC, and the chemical potential is maybe 20 hertz instead of 2 kilohertz, then you don't also have to worry too much about unequal particle number on 2 sides of the interferometer and the dephasing due to interactions. So these are the inherent advantages. On the other hand, what's also important in atom interferometry is to put in the work, which we haven't done. So what we have just done quickly is we split the box now in 2, and then we looked at 2 regimes. If you have a weak link between them, the phase stays locked forever. It's like 20 seconds or whatever. But even if we make them decoupled, what we find with basically 0 effort, that the coherence time is something longer than 100 milliseconds, which is actually already comparable to the state of the art with the harmonically trapped interferometers, where a lot more work has been put in. So maybe this is something to come back to and explore more. But meanwhile, we have switched to a different way of probing the coherence of the cloud and its ground state properties. So we use this method called Bragg spectroscopy, which, how many people know what Bragg spectroscopy? Yeah, no, you do. Okay, well, this is the basic idea, okay? And it's nice. I mean, it's a beautiful method anyway. It was I guess, for BEC first done by Wolfgang back in 1999. But there are neat things about doing it in a box, right, which we have kind of discovered along the way. You know. Why do we use this method now? So the basic idea is you have two beams shown on your cloud, and they have very, very slightly different frequencies. And so it turns out, you know, if that frequency is right, the frequency difference is right, then there's a resonant two-photon process. These beams are off-detuned, so there's no single-photon transitions. But detuned, so there's no single-photon transitions. But there's a resonant two-photon process where you absorb from one beam and you emit into the other beam. You pick up the frequency difference as the energy, and you pick up the so-called recoil momentum, okay, which in our case is something like, corresponds to something like 3 millimeters per second for the angle of our beams. Okay? And so you can already see here what's roughly going to happen. For a particular frequency difference, some fraction of the atoms gets Bragg diffracted, as we say, and travels at this recoil speed. Now, what are the conditions for this resonance? Okay, so the frequency difference F is the sum of these three terms here. The first one is trivial. It's a so-called recoil frequency. Is the energy you would have to give to an atom which is stationary and in vacuum in order to give it the momentum, the recoil momentum kick. The second part is sort of the Doppler effect, that if the atom already happens to be moving, then it sees the frequencies of these two beams slightly differently, right? And that shifts the resonance condition. And then the third term is that, like, when you go from the BEC into this recoiling state, you may change the interaction energy of the atom, and you also have to provide that by your laser beams, right? And this third term doesn't exist at all for the thermal cloud, but for the BEC exists because of the, whatever you call it, the exchange interaction term, the Hamburg-Brown-Tresek effect, the boson bunching, the bosonic factor of 2. Basically, like, because in the BEC all the atoms are identical, they feel interaction potential, which is just 1 times this, which is a bunch of constants, scattering length and BEC density. But once it's in a recoiling state, it feels twice as large potential, right? So there is an energy shift due to interaction as well, and that also has to be part of the resonance condition. Now, when you do this experiment in a harmonic trap, then every atom in principle has slightly different velocity along the recoiling direction, right? And also sits at a slightly different density of the BEC, okay? So it has this term different, and it has this term different. And so both of these effects lead to broadening of the Bragg line, okay? And additionally, some average of the last term leads to shift of the Bragg line. And so it's still possible to show that the BEC is quite coherent, but it involves a lot of post-processing and things like that. Now, in a uniform system, the nice thing is that the two things are decoupled, right? There is some sort of Heisenbergian, at least, spread of momenta in the BEC, and that's going to give some width of the line, okay? And there is also this shift due to interaction, but this is purely a shift. It doesn't lead to any broadening because the density is the same everywhere. Okay? So we can study the two effects now in a decoupled fashion. And hopefully observe directly something that is really just purely Heisenberg-limited over our distances, which are like 50, 60 microns, which is significantly larger than the distances over which you could prove explicitly coherence before with harmonically trapped gases. One little caveat to all this is that when you're doing spectroscopy, if you want to resolve a very narrow line, you have to have a relatively long experiment, okay? Otherwise, you Fourier broaden your signal. And there's two ways to think of it. One is like you calculate what line width you're hoping to get, and from there you get the time that your Bragg pulse has to be on. This is what everyone would first think of. But there's also kind of a many body point of view on it, and it gives exactly the same result, which is that basically, like, if you excite, say, in some semi-classical picture, if you excite an atom into recoiling state here on the left, okay, then the atom has to have enough time to travel across the whole trap before you turn off the Bragg beams if you really want to probe the coherence over the whole cloud. Because you have to have the chance to destructively being de-amplified and come back into the BEC. Okay? So in order to fulfill those conditions, what we do, it's a very simple trick, is we have this box trap, and we just make the walls lower than the recoil energy, okay? And so we have no problems with the clouds colliding with the recoiling atoms colliding with the walls, and you can make arbitrary long pulses. And if you've done Bragg spectroscopy before, Bragg spectroscopy pulses are usually something like a millisecond, and the frequency or less, and the frequency widths that are seen are in kilohertz range, right? So now that's going to be significantly less for us. So let's look at the results. So it's a very simple point of view now, very little processing needed or anything. So you have a real space picture. You take a picture of your cloud. You say it's yay big. Okay? This is the fit of how big it is, taking into account some imaging resolution, right? And then I say, like, okay, so the cloud is this big, say 30, 40, 50 microns, whatever it was in this case, right? So what is the absolute minimum Heisenberg uncertainty in the momentum? And then you can predict two things. This is the results. If you ask just an undergraduate to do it, he'll Fourier transform the top hat. They will get a sinc squared function. That's the red line over here. Okay? And then the blue line is a numerical calculation, which is a lot more effort, but very small difference. But just to make sure, the blue line is when you take into account that your pulse is not absolutely infinite in length, that you have non-zero Rabi frequency and things like that, right? But anyway, you can see that we're very close to basically, you could almost see the wiggles, but okay, so maybe a bit of a stretch. Huh?
So what you detect is lossless?
Sorry, what?
So what you detect there is lossless, basically? Because if you detect for a second, how can you detect that you have 10%? What are these points that you showed?
It's number of atoms in this diffracted cloud. So you apply a pulse. Sorry, what there?
So if you have something that is going on for a second.
35 milliseconds. The width is here. Sorry, maybe I said something wrong, but our pulse is, but it is coherent for 20 seconds. I mean, but the pulse is actually 35 milliseconds. This width is something like, I don't know, something. This one is maybe 200 hertz 0 to 0 or 100 hertz full width half max. It's about an order of magnitude narrower than what was seen before with BCs. Yeah.
So related to that are the Fourier transforms and the more sophisticated things that you're showing, they're already convolved with the pulse length. That is, they take into account the pulse length.
No, that's what the blue does.
The blue takes into
account the fancy. Maybe I shouldn't have said. Yeah, you already know, but like I didn't want to go into details. The fancy blue is taking into account the pulse length. Okay. But we have went deliberately to the limit where you don't have to rely on that. We didn't want to be very far from the red, but explaining it with the convolution, right? Yeah.
And is the shape the real shape or an idealized box?
It's an idealized box.
Okay, so that's another feature.
Exactly. That's what I'm going to make also the next slide. Exactly. Okay. So that's why I said, like, at some point, we prefer to explicitly compare with ideal box, and if there's any difference, it's there, than to say, like, we explain everything by numerically simulating our exact shape and, Yes. No, it's an idealized box. Yes. So that's exactly, that's another way to think of it. And that will come through on the next slide as well, which is almost my last slide. Okay, so now to quantitatively compare this, they have slightly different functions, right? So to compare them all, we just look at the full width at half max. And so this is the pre-spectral width that we measure as a function of atom number in a fixed box, okay? These are the two lines I showed before. So red is like just a simple sinc. Blue is when you take into account the pulse length, okay? And then for comparison, this dotted blue is what you would expect for an ideal gas. So remember, like, it's easy to forget. If I actually had an ideal gas in a box, the ground state would not be a top hat function. Sorry, I didn't want to do that. The ground state would be like half of the sign, okay? And that would actually have a broader momentum distribution. Okay? So it's only because we have interactions, and it takes just a bit of interactions to go into this simple, what we call Thomas Fermi profile, which in this case is just a flat top hat. And so what you see here is two messages, right? The first one is we are below the ideal gas limit, right? Because this is coherently swollen up the wave function in real space and hence shrunk it in momentum space. And B, it doesn't depend on atom number, which is another feature you expect for a box, which is different for a harmonic trap. Okay, and so then you can now vary the box size, and varying the box size is just typing in some numbers to move the walls. The tube stays the same, and you just move the walls, and then plot the width versus the inverse length, and so this is the Heisenberg scaling you expect. Again, red is the sort of the trivial sinc, blue is the responsible calculation, and the dotted blue is the ideal gas. Okay, so that's on the coherence, and then the last thing I'm going to show you, I'm already out of time, is we also looked at the interaction energy, as I was explaining a few slides ago. In a uniform system, there's a nice decoupling between the momentum spread effects, which affect only the width of the resonance, and the interaction energy, which affects only the shift of the resonance. Okay? And so here, sorry. Here you see this is a reference to some center, which is just called 0. But now I can actually now study what that center is compared to the recall frequency. Okay? And so we look at the shift of the Bragg resonance. And because our lines are so narrow, right? I mean, depends what you look at full width half max or sigma or whatever, but they're somewhere in the sub 100 hertz range, then we can fit the center of the line to something like 2 hertz, which corresponds to 100 picokelvin precision on the energy of the atoms. And so here, again, this is a fixed box size. We vary the atom number. We do two kinds of measurements. This is, you release the cloud first in the time of flight and then do the Bragg. In this case, the shift disappears. It doesn't depend on the atom number. And this is just a way to accurately measure your recall frequency, which for us is 975 hertz. On the other hand, if you measure in-trap, then even though the width did not depend on the atom number, the shift scales linearly, or maybe it's not perfectly linear, but we fit it with the simplest theory possible, again, in the spirit of our previous discussion. And assuming a perfect box, we predict this slope something like 24, 10 to the minus 5 hertz per atom. So we measure 23, 10 to the minus 5 hertz per atom. And so this is very simple. This last slide, at least. It's very simple mean field theory that explains this shift. But again, looking into the future, the nice thing about it, about these measurements, is that of all the things that we have discussed along the way, these latest measurements are the most stringent test of the uniformity of the gas, right? Because when we were saying like, that the critical temperature, for example, scales as if it was a box, that's proving that effectively the gas behaves as a uniform system on a 100 nanokelvin scale, okay? But now with this ground state studies, both the momentum distribution and the shift, everything is consistent with a perfectly homogeneous system, and we are down a sub nanokelvin scale, right? And now this is really scale which is even like j squared over u or whatever. I mean, if one day we now go on, or somebody else goes on to put some strongly interacting system into this box, then the box would be uniform enough for all these topological states, quantum magnetism and so forth. Yes, sorry, I have one more. I forgot. So we also studied something in between just for fun because these shapes are funny. So you can vary the time of flight as you release the cloud from the box, and then you can see how the shift gradually goes down and the width of the Bragg spectrum gradually goes up. There's no analytical solution for this, unlike the harmonic trap, where it was solved by Ivan Kastan and Ralph Doom some time ago. So we just did numerics, just mean field gross Pitevsky, and it matches quite well. Both the decay of the shift and the growth of the width, and also just what the clouds look like, this emergence of these diamond-like shapes in time of flight. Okay, and with that, I think I should stop. Thank you for your attention. This is just a summary of what I talked about, and also one personal advertisement. We're looking for a new postdoc because one of our postdocs prematurely got an academic job, so we need to fill that spot. Thank you very much.